Fructose is a 6-carbon sugar. It has a 5-membered ring structure which has 3 chiral centres and 5 alcohol groups. 2 are primary alcohols, 3 are secondary alcohols. It has a molecular weight of 180.158 grams per mole. Its CAS number is 57487. It has different names from fructose, levulose, fruit sugar or D-fructose. It has a density of 1.694 grams per centimetre cubed. It has a melting point of 103 to 105 degrees Celsius. In its solid form, it forms small white crystals and is soluble in water, alcohol or ethers. It is combustible in oxygen and, like all sugars, is a monosaccharide. It has the same empirical formula as glucose, which is C6H12O6, although it has a different arrangement in space. Now we're going to go into the kitchen. Fructose can be found in a wide variety of foods, such as confectionery products, soft drinks, canned goods, yogurts, berries, fruits, ice creams, honey, processed food and some roots like potatoes. Unfortunately, I think all my flatmates have eaten all of the food I was going to show you, so we'll move quickly on. The most common natural formation of fructose is from bees, and these bees will collect nectar from a plant. They will take it back to their hive and they will release certain enzymes, and they will turn the sucrose in the nectar from a disaccharide to its monosaccharides, and those are glucose and fructose. Any water molecules that aren't needed are evaporated. And the enzyme the bees use for this is called invertase. Glucose and fructose are present in roughly the same amounts in honey. Fructose or levulose gets its name because it reflects polarized light to the left. Fructose has 2 different kinds of isomers. It has beta-L fructose and beta-D fructose. The sugars we use today which we find in packets is sucrose, which you said before is like a disaccharide, and I don't know if I have any examples with me at the minute. Well, fructose is the sweetest of all the sugars and is much sweeter than glucose or cane sugars, and is often used in foods as much less of the sugar itself is needed to provide the same sweetness. However, although it is costly to manufacture and as large-scale production is very difficult, it has not been able to be fully utilised into the market. Now, if you see here, I've done a drawing and I've shown all the charges. As you can see, the oxygens are very negative, and these oxygens here are actually what goes into, what goes into these little stars here, which shows, as my key says, it becomes a nucleophile. The functional groups are all polar, and this acts like a base. Now with fructose, it also has hydrogen bonds, which are numbered here on the molecule. An example here is you've got water. The 2 lone pairs are attracted to the positive charge here on the hydrogen, and that means it's able to dissolve in water and such. The reaction I'm going to say is before with sucrose, if I can find it. Here we have forming sucrose, we have our glucose here, our fructose here, and it undergoes a condensation reaction between these 2 points here to form a bond, an oxygen bond here, and a H2O. Just quickly, in the manufacturing, industrially, to manufacture fructose, you take corn and soak it in warm water with a small amount of sulfur dioxide, roughly 0.1 to 0.2% sulfur dioxide, This helps separate different parts of corn, and it is milled to separate the starch from the corn. The starch is then concentrated, and with an enzyme, alpha amylase, the starch undergoes liquefaction, creating short-chain sugars. These are then reacted with glucoamylase to form glucose. The glucose is then reacted with isomerase to form fructose, and the reaction is an isomerization of fructose to glucose. And that's all I've got to say on my research project Fructose. I just want to say a special thanks to my cameraman, Joseph Mitchell, and I hope you enjoyed the video.